Okay, hello everyone. Today we will learn about the estimation part 4. I will go over rest of the sub-chapters in chapter 8. Okay. Chapter 8.8 is small sample confidence intervals for mu and mu1 minus mu2. Previously in chapter 8.7, we learned how we can derive confidence interval when the sample size is sufficiently large. Then we approximate the distribution with normal and derive the confidence interval based on normal distribution. However, if we have small number of sample size, in that case we can use different distribution. Let's try to learn this example. If we can assume that y1 to yn represent a random sample selected from a normal population, and we let y and s square represent the sample mean and sample variance, then theorems 7.1, 7.3, and definition 7.2 imply that this one follows the t distribution with n-1 degrees of freedom. Previously in chapter 8.7, if we have sufficiently large number of n, then this part, s over square root of n, this part converges to standard error of y bar, converges in probability. Actually, we will learn what this means in the following chapter, in chapter 9, I guess. And anyway, if n goes too large, then this thing converges to standard error, so we can approximate this thing with standard normal distribution. However, if n is not very large, then we need to use the t distribution to construct the confidence interval. Okay. So our t is defined this way, and this thing follows t distribution, which is this one. And actually, the t distribution is very similar to a normal distribution, so the derivation is also very similar. The only difference is that the t distribution have a little fatter tail than normal distribution. So if this is the normal distribution, t distribution have a little fatter tail distribution. Probably my drawing is not very good, but probably you can check the relationship between t and normal distribution by googling it. What I'd just like to emphasize is that t distribution, it have a little fatter tail, and actually the derivation is the same. So for 100 times 1 minus alpha percent of confidence interval, we can calculate it based from this probability. Probability of this thing equals 1 minus alpha, and if you put t here, and if you derive this thing with respect to mu, probability of mu is greater than something, less than something, then you can do it by yourself. I will leave it to you. Then you will calculate the lower bound and upper bound can be represented as this. And for tips to calculate this t, you can use R, because in this course runs online, and probably you are going to have an online exam, so it would be better to run code in R rather than finding table to find this value. So probably if you want to calculate t alpha over 2 with n-1 degrees of freedom, then in R you can just run this thing to get the number for this thing. Okay. For the one-sided one-sided confidence interval, it's also very similar. If you want to find the one-sided confidence interval, let's explain just for one case. This is for one-sided case, and if you if you put the definition of t here and solve it for mu, then you can find that this thing becomes this one. And from here, you find that this one is lower confidence bound for mu. So this one is 100 times 1 minus alpha percent lower confidence bound for mu. And similarly, if you do this one from different way, then you can find that y bar plus t alpha s over square root of n is the upper confidence bound for mu. Okay. Let's move on to example 8.11. A manufacturer of gunpowder has developed a new powder, which was tested in 8 shells. The resulting muzzle velocities in feet per second were as follows. So this is the data, and find the 95% of confidence interval for the true average velocity mu for shells of this type. Assume that muzzle velocities are approximately normally distributed. Okay, so they are approximately normally distributed, and we have 8 samples, and we want to find 95% of confidence interval. So our confidence interval can be represented as this: y bar plus minus t. Alpha is 0.05, so t 0.025, and here s over square root of n. So this is the formula for this, and to calculate this thing, I would recommend to use R to solve this, because if you are solving these problems in online, probably you can use R. So probably you just put the data to R. So set A equals the data, this thing, and then you can calculate mean of A and standard deviation of A. So our mean of A, which is y bar is 2959, and S, which is the standard deviation, this one is 39.0909. And what about T? This thing inside of the R, you can run Qt, 1 minus alpha and the degrees of freedom, and so if 0.025, so 1 minus 0.025, and since we have 8 data set, the degrees of freedom is 7, so the T, this value is 2.365, and the n here, this is 8. So if you put all the numbers, you can calculate the lower bound and upper bound. So if you put these numbers and calculate the result, then the result would be 2926.3 to upper bound is 2991.7. Okay, so this is our confidence interval. Okay, now let's move on to the finding confidence interval for the second case, mu1 minus mu2. Suppose that we are interested in comparing two means of normal populations, which is mu1 minus mu2, and we assume two populations have a common variance sigma square. In this case, to do the inference, what we know is that this thing follows the standard normal distribution Z. Um, however, we don't know the sigma. So from here, we know that this thing follows normal distribution because each of yi to y, y11 to y1n1 follows normal, y21 to y2n2 follows normal, and some of normal distributions is normal, so y1 bar, y2 bar both follows normal, and their subtraction also follows normal. And if you derive carefully, then you can find that this thing follows normal distribution with mean mu1 minus mu2 and variance of this thing. Okay, and from here, the unbiased estimator for the variance term sigma square is this thing, the pooled s square, and from here, let's let w as this one, and as we have learned, this one is from the first population, and we know that this one follows chi-square distribution with degrees of freedom n1 minus 1. And also, for the second part, this one follows chi-square distribution n2 minus 1. And this is sum of two chi-square distributions, and actually the first sample and second sample, the population samples from population 1 and samples from population 2, they are independent. And so this is sum of two independent chi-square distributions, and so the sum of them is again chi-square distribution with degrees of freedom is sum of those. And so W is again following chi-square distribution with n1 plus n2 minus 2 degrees of freedom. And as a result, to derive the t distribution, what we usually do is z divide by square root of w over the degrees of freedom. And if we put w and degrees of freedom and also z, then we can derive that this one can be simplified as this thing. So it's actually replacing the sigma as sp, and as we may prove it in the future, maybe in chapter 9, SP, the pooled estimator for standard deviation, it will converge it to sigma with probability. So for large sample, we can approximate this thing with normal distribution. And but for this chapter 8.8, since we have small number of samples, so we will use t distribution for this thing. Okay, so this one t follows t distribution with degrees of freedom n1 plus n2 minus 2. From the previous distribution, you can derive the 100 times 1 minus alpha percent confidence interval for mu1 minus mu2, this formula. And from here, t alpha over 2 is derived from the t distribution with n1 plus n2 minus 2 degrees of freedom. And one thing to note is this thing. In R, if you want to calculate this, the t alpha over 2 or z alpha over 2 or something, then it is useful to know that you can use q norm or qt or any q distribution something, maybe in the future qf, I don't know, but these are functions from R, and they are very useful to know. So in the future, if when you are working with homeworks or even for midterm exams, I think rather than looking at the table, since you are taking exam online, probably you can use R. So probably it would be useful to calculate this kind of T alpha over 2 using R. So check these notes. Let's move on to example 8.12. This one have very long script, but let's go. Example 8.12. To reach maximum efficiency in performing an assembly operation in a manufacturing plant, new employees require approximately a 1 month training period. A new method of training was suggested and a test was conducted to compare the new method with the standard procedure. So we want to compare the new method and standard procedure. Two groups of 9 new employees, each were trained for a period of 3 weeks, one group using the new method and the other following the standard training procedure. The length of time required for each employee to assemble the device was recorded at the end of the 3-week period. The resulting measurements are as shown in table 8.3, which is this one. So this is standard treatment and new training treatment. And estimate the true mean difference mu1 minus mu2 with confidence coefficient 0.95. Assume that the assembly times are approximately normally distributed, that the variance of the assembly times are approximately equal for the two methods, and that the samples are independent. Okay, so these samples are independent and they each follow normal distribution, and they have common variance factor. And in this case, the 95% confidence interval is derived to use this formula. And so the answer for this question is just calculating each numbers. And to calculate each number, I think it would be easier to use R. So inside of the R, you can put the standard treatment numbers here. In this example, I put them in A, and for new treatment scores, I put them in B, and you can calculate using R function, mean A or mean B, like this. And also you can calculate the pooled estimate SP using the formula and using R commands in here. And also you can calculate T alpha over 2 using QT command. And then at last, you can calculate the lower bound here and upper bound here. And so, as a result of calculating these things, the answer for this is minus 1.05 to 8.38 or something like this. So this is our confidence interval for 95%. And so this is summary for the section 8.8. For the parameter mu, if you have small sample size, and if all the samples, if we assume that all the samples following normal distribution, and if we assume the common variance, then you can find the confidence interval for mu as this thing, and here for t distribution, degrees of freedom is n minus 1, and for parameter mu1 minus mu2, you can find the confidence interval using this formula, and the degrees of freedom is n1 plus n2 minus 2. Okay. Let's try to solve one more exercise problem, which is 8.92. Solid copper produced by sintering, heating without melting. Okay, heating. Sintering a powder under specified environmental conditions is then measured for porosity in a laboratory. A sample of N1 equals 4 independent porosity measurements have mean Y1 equals 0.22 and variance S1 square is 0.001. A second laboratory repeats the same process on solid copper formed from an identical powder and gets N2 equals 5 and y2 hat equals 0.17 and the variance is 0.0020 and estimate the true difference between the population mean with confidence coefficient 0.95. So we all know the formula. We should use this formula, and then it's just how we can calculate each component. And actually, it would be easier to use R. So for the pooled SP square, for the SP square, using the formula, you can calculate it like this. So this 0.001, this is variance for the first group population, and this is N1 minus 1, and this is variance for the second group, and this is N2 minus 1, and divide by N1 plus N2 minus 2. And so you get SP square here, and the other is, you know that y1 bar is 0.22 and y2 bar is 0.17, so this is y1 bar minus y2 bar and minus qt, and the degrees of freedom is n1 plus n2 minus 2, which is 7, and our alpha here, alpha alpha over 2 is 0.025. From here, alpha is 0.05 and alpha over 2 is 0.025. So the 1 minus 0.025, comma 7, and we multiply square root of this thing and times square root of 1 over n1 plus 1 over n2. And so we get this number for lower bound and this number for upper bound. So our confidence interval is minus 0.013 to 0.113. Okay. And homework for chapter 8.8 are these. Next, chapter 8.9 is confidence intervals for sigma square. Previously we learned how we can derive confidence interval for mu or mu1 minus mu2. The next interesting thing would be the confidence interval for sigma square. So for the assumptions, we have a random sample y1, y2, yn from normal distribution with mean mu and variance sigma square. And we used s square to estimate sigma square, and we know that this one follows chi-square distribution. The n minus 1 times s square divided by sigma square. This one follows chi-square with degrees of freedom n minus 1 from theorem 7.3. And we can construct the confidence interval using pivotal method using this statistic. So the probability of this one this is the lower bound and upper bound, and since we know the distribution of this thing, we can calculate the probability. This is equals 1 minus alpha. One easy way to calculate the confidence bound is that setting equal tail probabilities. So this is the chi-square distribution, and we can set the equal tail probability. So this side we have alpha over 2, probability of alpha over 2, and this side as well, we can set the probability for alpha over 2. Then the probability of the inner part is probably 1 minus alpha. The probability for inner part is 1 minus alpha. And so we can calculate these numbers from the chi-square distribution. And so if you are using R, probably you can use Q chi. Q maybe I should check the function of R, but I will explain it later. Um, and if you rewrite this formula for with respect to sigma square, then you can derive this thing. And so this one is the lower bound for sigma square, and this one is upper bound for sigma square. So our confidence interval could be these two number. So here is the confidence interval. 100 times 1 minus alpha percent confidence interval for sigma square is this thing. And actually we derived it from the previous slide. Let's move on to example 8.13. An experimenter wanted to check the variability of measurements obtained by using equipment designed to measure the volume of an audio source. Three independent measurements recorded by this equipment for the same sound were 4.1, 5.2, and 10.2. Estimate sigma square with coefficient confidence coefficient 0.90. So we want to calculate the confidence interval with confidence coefficient 0.9, and we know as we know the formula of this, we will calculate each numbers. And to do that, I think it's easy to use R. So I recommend to use R to solve the examples or exercise questions for this online course. So we set our data as A equals 4.1, 5.2, and 10.2. And we can calculate the variance term, S squared term, with variance of A, which is 10.57. And also to calculate this one, chi-square of alpha over 2, and here alpha is 0.1. Alpha is 0.1, and so alpha over 2 is 0.05. And to calculate this term, we can use this thing, chi-skew 1 minus 0.05, and the degrees of freedom, which is n minus 1. 3 minus 1 is 2. So this is this thing is this, and this thing is this, and at last you can put all the numbers and to calculate the lower bound and upper bound. This is our lower bound, and this is our upper bound. So the confidential bound is the lower bound is 3.53 and upper bound is 206.4. Okay. Let's try to solve one more exercise problem, which is exercise 8.97. And suppose that S square is the sample variance based on a sample size n from a normal population with unknown mean and variance. Derive 100 times 1 minus alpha percent. A is upper confidence bound for sigma square, and B is lower confidence bound for sigma square. And previously we learned this thing. So to calculate one-sided, we can use one-sided probability. So for number A, we can use chi-square 1 minus alpha is less than or equal to n minus 1 s square divided by sigma square. This is 1 minus alpha. We only use the one side probability, and so from here, if we rewrite this thing, we can derive sigma square is less than or equal to n minus 1 s square divided by chi square 1 minus alpha. And this is the probability of this is 1 minus alpha. So this one is our upper confidence bound for sigma square. So this one is our upper confidence bound for sigma square. And similarly, we can calculate the lower confidence bound, and the lower confidence bound is n minus 1 s squared divided by chi square alpha. So this is our lower confidence bound for sigma square. So this is the formula for to calculate upper confidence bound for sigma square, and this is the formula for calculating lower confidence bound. Okay. And homework for chapter 8.9 are these. And homework for supplementary exercises are these. Okay, so this is end of the chapter 8, and so we will learn some mathematical properties of point estimator in the following chapter, in chapter 9. Okay, thank you and see you.